How big is a proton, really? In the energy filament theory, that innocent question becomes a stress test of whether particles are frozen parts or living structures that can adjust themselves. Experiments have chased this for decades with two main approaches. One uses electrons to touch the proton from the outside, and the other uses much heavier cousins of the electrons, called muons, to push in closer. You can think of them as two rulers, a light, flexible tape running around the surface and a heavier steel bar that presses straight into the middle. In standard thinking, as the techniques improve, both rulers should converge on the same answer. The error bars should shrink until they overlap because the proton is supposed to have one true size. Instead, the story refused to cooperate. Electron-based measurements keep pointing to a proton that is a bit larger, while muon-based measurements keep finding a proton that is noticeably smaller, with a gap of several percent between them. At the level of particle physics, this is not a rounding error. It is a "what does the inside really look like" disagreement. Different countries, teams, setups, beam energies, and analysis methods have attacked the problem. Yet the results still fell into a bigger camp and a smaller camp that stubbornly refused to merge. This persistent mismatch is what people call the proton radius puzzle. The mainstream attitude is cautious and sensible. Somewhere in this chain there are probably missing details, hidden systematics, or modeling gaps. With more work, the two values will eventually meet. The energy filament theory does not deny that possibility but adds one more question on top. What if both rulers are reasonably honest, and the thing being measured has a slight tendency to change under different probing conditions? In this picture, a proton is not an eternally rigid steel ball. It is a three-loop filament knot held up by the energy sea. 3 strands of circulating energy woven and locked into a stable pattern, and the sea's tension decides how tightly that knot is pulled. Higher tension pushes the loops closer and makes the knots more compact. Lower tension lets it relax and puff out a little. So, how big is the proton is no longer a single fixed number, but the answer that this knot gives under a specific tension and a specific way of being pushed. A piece of jelly on a plate makes the idea more concrete. Touch it lightly at the edge with a feather and it quivers but keeps almost the same outline. Shove it from the side with a stick and it visibly squashes and stretches, looking smaller in one direction and thinner in another, even though you never changed which jelly you were using. Electrons probes are like the feathers, light and looping at relatively larger distances, mostly feeling the outer charging pattern. Muons are like the stick, heavier and orbiting much closer in, piling more local tension onto the knot and pulling it tighter while they measured it. Both see the same proton, but they are effectively photographing it at slightly different tightening settings. So it is not shocking that the inferred radius comes out different. Seen this way, the proton radius puzzle does not have to be a pure question of who got it wrong. It could also be a hint that proton size is a softly evolving quantity that depends on tension and on how you poke it. If particles were truly hard-coded mechanical parts with geometry written once for all time, then no matter what clever tricks you used, both methods would have to converge on the same radius. Any remaining gaps would always be blamed on equipment. The fact that this particular gap has survived serious scrutiny for so long may be the universe tapping the table and saying, "These are not dead parts, they are filaments that can flex." From the energy filament theory viewpoint, the proton radius puzzle becomes our second nearby clue that particles react to their environment. The first was atomic clock drift, showing electron rhythms responding to tension. The second is this size mismatch, hinting that proton geometry itself makes tiny adjustments under different probing conditions. In the next steps, we will keep following these quiet discrepancies and ask whether other particle attributes, like lifetime, spin behavior, and magnetic strength, also gives consistent but slightly split answers in different experimental setups. Tap follow, share it on New Physics, Clear Universe.